All right, so this video is going to talk about attributes and graphing exponential functions. And so we're going to start by reviewing sequences. And so looking at the first example, we go from 6 to 10 to 14 to 18. The pattern here is adding 4 each time. And so we could continue this pattern and get 22. Next term would be 26. Next term would be 30. Because we are adding each time, this is arithmetic. Adding goes with arithmetic. They both start with A. And that number we're adding each time is called the common difference. Okay, that number is 4 in this case. I'm going to skip the formulas. We don't need them for what we're talking about today. This next example, we're going from 2 to 6 to 18 to 54. And so this one's actually multiplying by 3 each time. And so we call this a geometric sequence. We can continue multiplying by 3 to get the next few terms. I'm going to skip that because those are large numbers. And so instead of calling it a common difference, we call it a common ratio. And that common ratio in this case is 3. And so we talked about how arithmetic sequences correspond to linear functions. Geometric sequences correspond to what we're talking about today, and that's exponential functions. It's a common ratio, meaning we are now multiplying instead of adding. And so there are 2 types of exponential functions. There's exponential growth and exponential decay. Exponential growth approaches either positive or negative infinity. Okay, and then exponential decay approaches a flat line. And in our case, in Algebra 1, it approaches 0. Okay, so a curve that never touches but gets closer and closer to a line called an asymptote. Asymptote. So, for example, 0.1, 0.01, 0.001, 0.001, that's getting closer and closer to 0, but never actually equals the 0. It just gets infinitely close. This introduces a concept in calculus called limits, but it's just the idea of approaching a number but never actually equaling it. It's going to look like it, but it doesn't. And so let's look at some pictures. And so looking at the purple and green, these are 2 examples of exponential growth. We always read our graph from left to right, always. And so if you're climbing along these curves, you are moving away from the x-axis. That's what growth is. Okay, growth is away from the axis. In the purple case, that's positive growth because it is above the x-axis, whereas the green would be what we call negative growth because it's below. So in this case, positive is above, negative is below. Okay, and so in all cases, well, let's just fill in this part right now. The purple graph is approaching positive infinity. It's going up to positive infinity, whereas the green graph is going down towards negative infinity. The domain for all exponential functions is all real numbers all the time. Kind of like quadratic and linear. The three functions we talk about are linear, quadratic, exponential. The domain for each of these functions is all real numbers all the time. Makes it super easy. So we can go ahead and fill in these two. All real numbers. All real numbers. Okay. And so the range actually depends on whether you are above or below the asymptote. So let me get a good color here. So the asymptote is where the function makes a flat line. So find where it looks flat and see which y value that is. In this case, it's y equals 0. And for algebra 1, it's typically always y equals 0. So the asymptote is y equals 0 in both functions. The purple is flat at the 0 mark. The green is flat at the 0 mark. And so both have an asymptote of y equals 0. The range of the purple graph, this purple graph is above, so we're going to say y is greater than 0 for the range, whereas the green graph is below, so we're going to say y is less than 0. So remember this trick, below has a less than sign, below. So anytime it's below, you want a less than sign. Okay, so looking at our decay graphs, remember we're still reading the graph from left to right. Okay, and so if you're on this curve, you are flatlining as you go to the right. Same if you are on this curve. You start way down here, but then you're going to a flat line. Anytime you're flatlining, think of like a heartbeat. If the rhythm of your heart rate or whatever is going to a flat line, it's dying, it's decay. And so both of these are approaching the y equals 0 line, which is still the horizontal asymptote here. Okay, so y equals 0, y equals 0. And then for the range, the blue graph is above. The orange graph is below. It's below. So even though they're both approaching 0, only the orange gets the less than because it's below the graph. Okay, so we're going to look at some examples. And so you can actually graph any equation you are given in Desmos, but you can also just look at the equation and get some valuable information. This a value in the equation, the number in front of the parentheses, is always going to be your y-intercept. Sometimes they call that the initial value. Whereas the b value, let's use red, the number in parentheses being raised to the x power is you can call it a common ratio like we do for sequences. They also call that the growth or decay factor. And if that b value is greater than 1, so for example, 2, 3, even 1.5, or even 1.1, as long as it's a number bigger than 1, let me get a fraction on here, like 3/2, that would be bigger than 1. It is going to be growth. Whereas if it's it's never going to be negative, but if it's between 0 and 1, so like 0.2 or 1/2, 2/3, even 5/6. That's going to be an example of decay. You're never going to have a b value of 1 because then it wouldn't be growing or decaying. It would be flat. That would be linear. And you're never going to have a negative b value. That would not be an exponential function. It would just be a crazy oscillating set of points. So never negative, never 1. Only positive, above 1, or a fraction. Okay, so if we look at these examples, this 4 is going to mean this function is growth because 4 is greater than 1. This 3/2 is bigger than 1. It's 1.5, and so this is going to be growth as well. This 2/3 being raised to the x power, that's less than 1. And so this is going to be decay. This 0.2 is less than 1, so it's going to be decay. This graph, we always read to the right. If you're traveling to the right, you are approaching this flat line, so it's decay. Oops. This one, as you go to the right, you are moving away from the 0 line. So this is growth. Even though it's negative, it's growth upside down, but it's growing away from the 0, away from the x-axis. Okay, looking at this table, it goes from 0.16 to 0.8 or 0.16 to 0.8 to 4 to 20 to 100. So this is getting multiplied by 5. And so that's definitely growth. It's growing. If we were to graph that, we would see it growing exponentially. Here we go from 200 to 20 to 2 to 0.2. That is decaying if we were to graph those points. So decay. It's going to 0, getting closer and closer to 0. Okay, and so it says identify the y-intercept and determine if it represents growth, exponential growth, or exponential decay. We just did that. Okay, the other part we haven't done is the y-intercept. So in this case, the y-intercept is 3. In this case, the y-intercept is 1/2. In this case, the y-intercept is 10. Sometimes they just say the value. I'm going to write it as an ordered pair. I think that's a good habit. 0, 1.5. In this case, we have a graph. We see it's 0, 3. Here, I believe that is -5. And then here in our table, looking for where x is 0. Here, y-intercept is 2. All right, next set of examples. Find the following attributes given the exponential equation or graph. Okay, so starting with this graph, growth or decay, as we go to the right, it is going away from the axis, so definitely growth. Y-intercept is 0, 3. Common ratio, we got to figure out what it's multiplying by. And so we go from a value of 3 to a value of 6. That's multiplied by 2. And so our common ratio is 2. If you ever need to calculate it, if it's not a pretty number like 2, take the second y value, which in our case was 6, and divide it by the first, which was 3. And that will give you your common ratio. Okay, and so now we have everything we need for our equation. The y-intercept is your a value, and the, oh, sorry, that is not the y-intercept. The y-intercept is your a value. and your common ratio is your b value. And so to write our equation, it's a times b to the x power. A goes here, the common ratio goes here with the exponent. Domain is all real numbers all the time. And then for our range, we need to know where the asymptote is. So go to your graph and look at where the flat line is. And so here we're flatlining. So we're just going to continue that flat line to the y-axis, and it's at y equals 0, which is usually going to be the case for us. And then since our graph is above this line, we are going to say y is greater than 0 for the range. Okay, here we don't have a graph, we have an equation, so we can fill in some of it. We'll want the graph for the range and asymptote. Okay, and so just looking at this common ratio of 1/2, since that is less than 1, we know it's decay. 1/2 is less than 1. This 4 is our a value, so that's our y-intercept. Oops. You can say 0, 4, or if they're calling it initial value, you can just say 4. And then our domain is all real numbers. And then now for the range and the asymptote, this is where you're going to want Desmos so you can see what the graph is looking like. And so we want to type in either y equals or f of x. I'll do f of x. For parenthesis 1 divided by 2, and then get out of the denominator, close your parentheses, and then click the A to the B button and type your x. Okay, and so here, see my y-intercept at 0, 4, and we can tell that it's obviously decay as it goes to the right. It's going to a flat line. The flat line is at y equals 0, and the graph is above that line. So asymptote is still 0, and we're still above, so y is greater than 0. Okay, here we don't have an equation, but we can write one after we look at what's happening in the table. So we can get our y-intercept right off the bat. And then let's just look at the whole numbers, not the decimals. From 7 to 21, that's multiplying by 3. And then from 21 to 63, that's also multiplying by 3. So our common ratio is 3. And so that is growth. It is getting multiplied by a number bigger than 1. And so now we have everything we need for our equation. The 7 goes here, the 3 goes here, raised to the x. Domain is all real numbers all the time. And then now that we have our equation, we can use Desmos. Okay, so f of x equals 7 times 3 raised to the x. There's our graph. It is clearly growth. Our flat line is at 0 once again, usually the case. And then this green graph is above that flat line. Okay, and so you don't have to graph these by hand since we'll have Desmos, but I do want you to be able to identify this information. A lot of people get confused by this 2 to the x because there's no parentheses. If you want, you can rewrite it inside the parentheses, raised to the x, and then the initial value, there's usually a number here. If a is 1, they don't usually write it. Okay, so in this case, our y-intercept is 1, and our growth factor is 2.